Now in this session, more details, quite a few little details. You're not really expected to be able to derive them fully. It's more just giving you a taste of higher things at higher levels. Alright, so let's see. So where were we? We were trying to find the expectation value of little f of r. And why were we doing that? Because we needed that to find the change in the energy eigenvalue of the Hamiltonian when this extra term, this perturbation to the Hamiltonian due to the spin-orbit coupling. Right. So whole chain of reasoning. So how to find the expectation value of f of r. To find the expectation value, you've got the operator f of r, and you need a wave function. And as saying earlier, the wave function is just big R with suffix little n r, and we've done that from earlier sessions. Okay, so that's here. We did that, previous chapter, so we know what this is. Now, you can try doing this stuff if you like. I haven't even bothered putting down HW because it's getting tougher. It's more like I say, just giving you a taste of what higher level quantum mechanics is about. This is an introductory text. It's like first, if this is the first time for you doing quantum mechanics, then this is an introductory text suitable for you, as it says. Okay, now if you given the the use of this, your f of r formula, which we had from the previous session, and it works out that the expectation of f of r is 0 if L is naught. Is that obvious? Is that intuitively obvious? No, not immediately. So these results in a sense just thrown at you. But if you care to try to calculate them, I can really literally do. I can take my hat off too. All right. Now for the angular momentum little l, if it's greater than 0, if it's non-zero, then it works out the expectation value times h bar squared is this rather complicated expression. Right? And where that comes from, not immediately obvious, but and it's certainly not given in the textbook. Right? It's just thrown at you. But it's given here, I assume, to explain the phenomenon of doublet, and I'll come to that in a minute. All right. Also, it introduced now this term here. This is new. So this alpha to the fourth power. N is just the ordinary quantum number for the level of the energy level in the hydrogen atom, let's say. So N1, 2, 3, whatever. L's, But this is new. This alpha, what is it? Well, it's defined, 3 bars. It's defined as the square of the charge in the electron divided by 4 pi eta. This eta comes from the Coulomb potential equation, right? H bar c, speed of light. Now, this alpha keeps popping up, especially in quantum field theory, the quantum mechanics of interaction between charged particles and the electromagnetic field, QFT, this alpha. So it crops up enough, and it's quite significant. So it's given its own name, it's given a label, and it's called the fine structure constant. And fine structure, well, you'll see why it's labelled that in a minute. well, I can give it to you just quickly. Fine structure in the sense you're looking at fine changes, small changes in energy eigenvalues, due to spin-orbit coupling and other small effects. Okay? So fine, you're looking at the fine structure of the energy spectrum, the spectral lines. If you have measurements very accurate, looking at the actual frequencies, the energies of the photons coming out when you're looking at an atom's or an element's spectra, meaning all the frequencies that come out of the photons that come out, and you look at the fine details, like you might have a sort of fuzzy line in the spectrum, but then you use more accurate measurements, and you'll find that fuzzy line splits up into sharper lines, but quite separate, maybe by small frequencies, but separated nevertheless. So the energy differences are fine. So you're looking at the fine structure of the spectra. Okay? So this crops up in the analysis of spectra. So it's often called, it's called the fine spectra constant. And interestingly, this quantity, this alpha, is dimensionless. I've talked about dimensionless quantities before. So if you put in all the dimensions, but that is, what do I mean by dimension? It's some power of L, M and T. L is length, like meters, time in seconds, and mass in kilograms. Okay. For example, the dimension of velocity, now that's distance over time, so that would be, its dimension would be L times t to the minus 1, length over time, that's velocity. Acceleration, its dimension would be L times t to the minus 2, right? Because what's acceleration? It's the change in velocity over, change in speed over time. Okay, so its dimension would be L t to power minus 2, and so on. Density, what would it be? Now what's density? It's like the mass per unit volume. Okay, so the density, the dimension of density would be m times L to the minus 3. Follow that? Because L to minus 3 is 1 over the volume. Okay? Well, this quantity alpha here, the fine structure constant, if you actually work it out, you're putting in all the dimensions of all these things, all these factors, it works out to be dimensionless. Right? So it's L to power 0, M to power 0, T to power 0. And for decades, this fine structure constant has fascinated physicists because it seems to give clues to future physics. And why do I say that? Well, the fact that this is dimensionless implies, presumably, there's some relationship between charge, the speed of light, and Planck's constant. So, in other words, the charge has something to do with the electroweak force, right, as I was talking about earlier. C, speed of light, so it's relativity, and H, Planck's constant, quantum mechanics. So the suspicion is that this fine structure constant is some kind of clue, indicator, that maybe not, there is some glorified, unified theory waiting in the future that explains why this fine structure constant is dimensionless by relating these things, the electroweak force, relativity, quantum mechanics, and so forth. Now, you may know one of the great dreams of physicists for the 21st century is to unify, to find a unified theory that explains the existence of the four main forces, the four forces in nature: the gravitational force, the weak is going up in strength, the weak nuclear force, the electromagnetic force, and the strong force, strong nuclear force, binds the quarks together. Okay, and that theory would explain the existence of these four forces, what they are, what their strengths are. It would explain the masses of all the elementary particles, what their interaction laws are. So that's the big dream. It was the dream of Einstein in the last 30-odd years of his life, after he dreamt up general relativity in the mid-tens, 1915, 16. Then until he died, he was pursuing the dream of unifying electromagnetism with gravity. Now, he largely ignored the quantum, because he had quantum mechanics. He didn't like the philosophy of quantum mechanics. So he largely ignored the other two forces, which are a big mistake. A lot of people think the weak nuclear force and the strong nuclear force. So, but the general notion of trying to unify a TOE, a theory of everything, that's still very much the big dream of theoretical physicists. And the hope is that string theory maybe is that great unifier, that TOE. For example, string theory already, it just drops out. It's a consequence of string theory that Einstein's general theory of relativity just comes out of it. Right? So general relativity is a consequence of string theory, and so is supersymmetry and various other things. So the big hope is that string theory may be that unifying theory. Anyway, okay, push on. So there's a whole story behind the fine structure constant alpha here, right? Which is roughly of this value, dimensionless, just a number. It's a number with no LMT dimension at all. Okay. Right. So we solved for the expectation value of FR. We got this rather complicated expression. So we can plug this in, the FR h bar squared. We can plug it into the formula we had in the previous session, delta E. Well, delta E was expectation FR h bar squared, and then all the J's and the L's and the S's in square brackets. So here it is here. So that means this and this just comes from here, right? Times this. So here's your correction now for the eigenvalues of the energy for the Hamiltonian. Okay. Now, probably why my guess is that the author, Davies and so on, have put this in because they want to tell you that this term here leads to a shift in the energies, the observed energies, when you compare to what you'd calculate without the spin-orbit interaction. Okay. Now we're talking